Hello and welcome to Lecture 14. This is our last lecture for the Winter 21 semester. In this lecture, we'll look through extending our understanding of quantum physics. With that, we'll introduce Beer's law and also look at the Compton effect and the experiments that allowed the expansion of quantum theory. We'll finish by investigating several of the different applications to spectroscopy, looking at the ways we use our knowledge of quantum physics to better understand the substances we are investigating. In our early look at quantum theory, we saw that there was the photoelectric effect that was better defined by treating light as if it acted like a particle. At the time of its discovery, still many scientists believed the photoelectric effect was just a more nuanced application of wave theory. At that time, Einstein proposed that the photon would carry a momentum, and that could be calculated using Planck's constant and the wavelength. But experimental evidence of this needed to be sought. The Compton experiment found this. So the Compton experiment involved firing photons at other atoms, and at times what was seen was that the energy and the frequency of the photons would be unchanged when the photon transferred straight through the atom. But other times the photon was found to be off to the side, or it would have changed its direction of travel. When this happened, the energy or the frequency were changed as well. The important part here is that the amount of change could be predicted using the classical conservation of momentum approach to collisions. This was evidence that there was a momentum involved with the interaction that the photon had with the electrons of the atom. This Compton scattering supported the momentum theory, which means it supported the particle theory of light and further cemented the theory that we had to treat light with a dual behavior of wave nature and particle nature. One of the other consequences of supporting the fact of the duality of light led some scientists to theorize that if light behaved like a particle and had momentum, then possibly matter behaved like a wave. It was theorized by the scientist de Broglie that a matter wavelength could be calculated. So in this case, we see this as a probability. So if we picture an electron in the Bohr model, the true belief is that the electron's position has wave-like properties. We have areas of high probability of observing electrons and areas of low probability of observing electrons. And this is due to the fact that the electron has that slight oscillation movement associated with a wave. So de Broglie's matter wavelength can be calculated using the same equation that we saw previously. So the matter wavelength calculation for something like an electron would just be Planck's constant divided by the momentum of the electron. And because the electron has a mass that we were able to measure, we can calculate that momentum. Now, for particles with mass much greater than a subatomic scale, these wavelengths are extremely small and very difficult to scientifically observe. So we can see these wavelengths at the electron level, we have seen them at the proton and neutron level, but when you start doing calculations to try and determine what they would be for things the size of a baseball, they start to have a very, very small magnitude. What this means is that with a wave-like behavior, while we can use classical collision physics to describe what will happen with interactions on electrons, it introduces a probabilistic nature. Because the electron has a position, but we don't know that position perfectly, we could set up a collision and sometimes it'll occur and sometimes it won't. We're going to keep this in the back of our mind and we're going to move on and start to look at some of the applications of quantum theory to our investigations. We're going to take a closer look at the visual spectrum of light that we saw last week. Remember, the visual spectrum is a continuous spectrum where we have colors of light associated with different frequencies. Because light behaves both as a wave and a particle, we can calculate energy that particle would carry using the equation E is equal to hf. And remember that energy and the wavelength of the particle are inversely related, and we can also calculate that. So on our red end of our spectrum, we have low energy and wavelengths of approximately 700 nanometers. And on our blue end of our spectrum, we have high energy with wavelengths of approximately 400 nanometers. So what we're going to look at now is the light that's put off by certain substances, the emission spectrum, and the light that passes completely through certain substances. And we refer to that as the absorption spectrum, and we're going to look closely at these in their explanation to understand why they're referred to as these things. Now, when we complete some spectrophotometry, this is kind of a good sketch of what we're looking at. So we begin with some sort of high-powered source, and this source will put out white light, which is light of all wavelengths. And then we shine that light through lenses and our substance. Now, the lenses are used to spread the light out so that it covers all of the substance that we have, and then focus the light back together again so that we can properly refract it. Now, as the light passes through our substance, as we saw before, some wavelengths are absorbed based on how much energy they're carrying and the interactions they have with electrons in the substance. After traveling through another lens to refocus, a slit to begin the expansion progress, and a lens and a prism to refract the light to separate the wavelengths, we would be able to observe all of the wavelengths that were able to pass all the way through our sample. We're going to bring in that image of the absorption spectrum. Now you'll see here is we have this visible spectrum of light, and this is what we would observe at the far end of our spectrophotometry. And you'll notice that there's black lines all through this. These are our missing wavelengths of light. This is what we're referring to when we're talking about the absorption spectra. Each of these black lines are spectral lines corresponding to an energy level that our substance was able to properly absorb. You should recall that when we talk about absorbing energy associated with wavelength of light, we are thinking of a nucleus and its energy levels for its electrons, and that if it was able to absorb a photon, it could take an electron from the first energy level to the second, or the first to the third, or the first to the fourth. This was the transitions associated with absorbing a photon. After some time, the electrons at the higher energy levels will want to fall back to the lowest available energy state. And you'll see here, represented by all the pink lines, is that there are many more possible transitions from higher levels to lower levels than there are from lower levels to higher levels. This is because when electrons are stable and haven't been excited, they often want to be at that lowest level. So there aren't electrons in the third energy band to be excited up further. Because of the tendency of electrons to remain in the lower levels when they're not excited, and then excite up to the highest levels, and then the possibility that they don't fall all the way back down to the lowest level immediately, means that there is often a greater emission spectrum than there is absorption, because there's many more variety of emissions that could happen. Let's bring up that emission spectrum again. So here, this emission spectrum is bright lines among a noisy but dim background. So we note that it's not a perfect sample. We still get some light that passes through to our sensor. Now, the fact that emissions are often delayed is what we're going to talk about here. But first, note that every time we have an emission that is not directly associated with a previous absorption, that emission will be at a longer wavelength because it's at a smaller energy. So we could have gone from 1 all the way to 4, takes a lot of energy in, but when we go from 4 back down to 3, we're only emitting a small amount of energy, so we would have a longer wavelength. Let's go back to that delayed effect. The delayed effect is referred to as fluorescence. So fluorescence is the emission of energy at a delayed point in time after an excitation. We have several different types of fluorescent reactions, but when we talk about emitting an energy, we may use that word fluoresces, instead of emits. Let's take a moment to look at a spectra example, albeit a fairly simplified one. If an ultraviolet, that's a 350 nanometer wavelength, is absorbed, how much energy was absorbed? So part one, we have our wavelength, 350 nanometers. Remember, we have our energy equation, E is equal to Planck's constant multiplied by the frequency. And we also know that because we're dealing with light in the electromagnetic spectrum, we have C is equal to wavelength times frequency. Rearranging the second equation and substituting it into the first, we find that we can calculate the energy from Planck's constant, the speed of light, and the wavelength we were given. So plugging in our values of 6.62607,004 times 10 to the negative 34 joule seconds, and the speed of light at 2.9979245 times 10 to the 8 meters per second, and dividing that by 350, but instead of nano, we'll write times 10 to the negative 9 meters. And calculating, we get 5.67555498 times 10 to the negative 19. If we consider our units, we have seconds canceling with the per second. We have meters on the top and meters on the bottom. So luckily, our energy comes in units of joules. We only have two significant digits here, so this is approximately 5.7 times 10 to the negative 19 joules that were absorbed with this one wavelength. Let's look at part two. If the atom then fluoresces 4.174 times 10 to the negative 19 joules of energy, what is the wavelength and color of the emitted photon? So in part two, we're given energy. I'm going to rearrange the equation we created in part one. So now it says wavelength is equal to Planck's constant multiplied by the speed of light divided by energy. We're going to substitute those same two constants up top. We are going to divide by our energy of 4.174 times 10 to the negative 19 joules. And if we plug this into our calculator spits out this value, 0.000000475. Remember, we're talking about wavelengths here, so while this would be a scientific notation value of 4.75 times 10 to the negative 7, I'm going to move my decimal place two further places so that I can say this is 475 times 10 to the negative 9 meters, which is approximately 475 nanometers. And if you consult the chart on your formula sheet, this would be blue light associated with a wavelength of that length. Let's look at how we apply the fluorescence effect. Now, if I shine some ultraviolet light on a piece of DNA, the spectral that is emitted by the DNA, or the spectral that makes it through, is actually quite complex. And a lot of the substances we look at, especially when it comes to DNA or organic compounds, are very similar spectrally. So it's difficult to use the fluorescence effect to determine different substances directly. Instead, what we do is we pick dyes or dye agents that have a specific behavior around certain substances. So a dye agent will bond to some substances, but not others. Then, when we expose the dye agent to ultraviolet light, the dye that has bonded to the substance we want to know of its presence will absorb the ultraviolet light, and then later it will fluoresce light out. Now, because it fluoresces light at a longer wavelength than it absorbed it, we'll actually see it'll be in the visible spectrum instead of the ultraviolet spectrum. And this fluorescent glow would then identify the presence of our substance of interest. Even the absorption spectral analysis is difficult to pinpoint. To date, we keep doing examples that involve one photon. In practicality, it's difficult to isolate and observe just one photon. A 100-watt bulb emits approximately 100 billion photons every second. So that's 1 times 10 to the 20 photons per second. When we think about the function of what we've looked at in the past few examples, it's happening many, I think you get the point, times per second. So what we want to actually look at is the percentage of these that are absorbed, and that's going to help us get an idea of what kind of interactions are happening. So in spectophotometry, what we do is we have a substance or a sample, and we're going to shine an incident light on it. Some of that light will make it through, but some of it won't. But the Light that makes it through is referred to as a transmitted light. It's been able to transmit through the substance. Rather than trying to understand the individual energies that have transferred through the substance, we use the amount of energy that transfers through the substance to give us an idea of sometimes what the substance is and other times the concentration. Recall from earlier in the lecture, we have that probabilistic approach to interactions between photons and electrons. This is another reason why trying to consider this as firing one photon through a source doesn't work, because there's that possibility, or it's more likely, that the photon goes straight through the atom and the substance and doesn't interact with any of them. So by using the spectophotometry and the comparison of intensities, we deal with that low probabilistic interaction that we've just talked about. This comparison of the amount of intensity that gets through a substance to the amount of intensity that was incident on the substance is called transmittance. And we have the equation T is equal to IT over IO. So T is the transmittance. The IO on the bottom is the intensity of the incident light. And for this example, we're going to measure that in photons per second. And IT is the intensity of the transmitted light, again measured in photons per second. I think you may notice here that if we're measuring in photons per second and photons per second, that T will not have any units. It's just a ratio. And the other thing is that because the light that gets transmitted through will always be less than the light that was incident, unless some odd reaction happens, this value will also always be less than 1, or should be less than 1, and as it's a ratio comparing something that is always smaller on the numerator to something that's always bigger on the denominator. So now we'll look at an example. And again, we don't typically measure intensity in terms of photons per second, but this example illustrates what transmittance means. So if a spectrometer beam emits 140 times 10 to the 18 photons per second, and we detect 56 times 10 to the 18 photons per second after passing the light beam through the analyte, what is the transmittance and its percentage? So transmittance is equal to the comparison of intensities. The intensity that we detect after is the 56 times 10 to the 18. The intensity of the incident, which is our denominator, is 140 times 10 to the 18. Our magnitude and units will cancel out here, so we're really comparing 56 to 140, and we get back that we have a transmittance of 0.4. This is a ratio, so if we multiply it by 100, this tells us that roughly 40% of the light makes it through the analyte substance. With a transmittance of 0.4, we're able to consider something more important, the absorbance, which is the amount of light that the substance, the analyte, was able to block. Now we have this equation. A is equal to negative the logarithm base 10 of our transmittance. The absorbance actually increases exponentially with some features. So we need to have this logarithmic function to make this a more linear relationship. We need to take a quick review. I'm not sure how comfortable you are with logarithms, but you need to understand that a logarithm answers the calculation. Which exponent, a here, do I need to raise the base, 10 in our case, to in order to have a result of t? This is really just a rearrangement of the equation 10 raised to the exponent a is equal to t. And using logarithms is our way of applying something similar to algebra to solve for that value of a. Remember, in our application, t is always less than 1. So in order for us to have the result of this exponential equation, our exponent will always be negative. So we develop our absorption formula with that negative in front of the log to make sure we always get a positive value for absorption. So using our previous example, we see that the absorption will be equal to negative the logarithm base 10 of the 0.4 transmittance. And if we plug this into our calculators, your calculator should have a log button. And note how it doesn't have a 10. Calculators always assume that the base logarithm you're working with here is 10. If you need to work with a base of e, remember that's the ln button right beside log. But we'll be using log. So we press the calculator button of log of 0.4, and we see that it gives us a negative value because I forgot to type in the negative. So we can write down that our answer is 0.397940008. And while significant digits with exponents is a little tricky, we'll just keep 4 of those digits for now. So this is approximately 0.3979. Now, the reason we did that is because Beer's law allows us to connect the absorbance of a substance to a concentration of that substance. So if we think of the equation, A is equal to epsilon multiplied by L multiplied by C, where A represents the absorbance, E represents the molar absorptivity, and this is going to be known through experimental results, and it'll come with different possible units, but often it's liters per mole centimeters. You have to pay attention to what your source is telling you though. And here in our equation, L is just the length of the light path through our substance. It's often just our test tube diameter, and you're going to have to take a moment to ensure that your units that you measure the test tube in correspond with the units of your molar absorptivity. And then C is the concentration. The way we often use these formulas is that we measure a transmittance, which lets us calculate an absorbance, and then we'll go to a chart for the substance and we'll look up the absorbance that we calculated, and that'll take us over to a reference line and lets us understand what our concentration of this substance is. And the reason we're able to do that lookup is because there's been experiments done to find standard concentrations and absorbance connections for the material. So you'll note that using spectrophotometry this way is a way of determining a concentration of a known substance. The reason we do this is it's a little less invasive than other methods we have for determining concentration. Let's consider an example for Beer's law. We know that the molar absorptivity of an analyte is 6.27 times 10 to the 4 liters per mole centimeters, and the transmittance through a 1.2 centimeter test tube is 0.6. What is the concentration of this substance? Well, recording what we know, we have an epsilon value, the molar absorptivity of 6.27 times 10 to the 4. Notice the connection here with the units. Liters over top of moles and centimeters is the same as moles raised to the -1, centimeters raised to the -1. We have a length of 1.2 centimeters, which is okay. So we take a look and see that our centimeter length lines up with the per centimeter molar absorptivity. We were told there's a transmittance of 0.6, and we're trying to find the concentration. We use our two formulas that we have here. A is equal to epsilon times L times C, and at the same time, A is equal to negative log base 10 of T. We can set these two equations equal to each other. We can rearrange for the concentration, and we can substitute our values. So we're going to calculate negative log base 10 of 0.6 divided by 6.27 times 10 to the 4 divided by 1.2, and we see we get a result of, and again we have to be careful, if we look at our result, this is 6 total zeros, so we need to have 2.94 times 10 to the -6. If we consider our units, this will be moles per liter. Let's take a moment to recap our lecture. This lecture, we investigated further applications of quantum physics. We examined the ways we use the quantized behavior of light to examine substances. We saw that this often relies, though in different ways, on the measures of the absorption and emission of energy for each substance. Sometimes those are precise measures, and other times we are just looking for the effect to exist itself. We applied this understanding of absorption and emission to investigative techniques, and we even introduced a new law, Beer's law, and connected it to a method of non-invasive concentration analysis.